Welcome back to Unit 5. Before leaving on break, we were starting to talk about definite integrals. And what we saw was a discussion of how integral notation, which looks like this elongated S, is a way to represent the area under a curve. And in class, we talked about how actually the area under a curve, if we think about the curve as being the derivative function, is related to the total change in the original function, as in the y value of the second point minus the y value of the first point. This was actually the first part of the fundamental theorem of calculus, which we'll come back to at the end of this unit. We also talked about in class evaluating integrals by thinking about areas, and these were the examples we looked at. What happens when you have a function that is just a straight line, when it's a linear function, and when it's a shape. Sometimes you can't just use area formulas though, and so we ended our discussion in class by talking about antiderivatives. We're going to go into antiderivatives in much more detail, but first I want to talk some more about properties of integrals and integration. By the end of this video, you should know 5 key properties of integration, and you should be able to use them to evaluate an integral without necessarily using an antiderivative, just based on understanding the area that we're talking about. Great, so let's get started. The first 3 integration rules are pretty simple. Pause the video here to write down these 3 rules, including their title in red. You can judge whether or not the blue is going to help you. When you press play again, I'll explain what I think these mean. Okay, so these are 3 very simple rules, and they're really kind of just helping you get to know the notation. The order of integration is a rule about the order in which we list the endpoints. Normally, we're used to calling a the variable for the first or lesser x value of the region in which we're trying to calculate the area. So let's say we were calculating the area from 2 to 8. 2 would be a and 8 would be b. You don't necessarily have to write the smaller number on the bottom, however. In particular, if I know what the area is from 2 to 8, then the integral from 8 to 2, switching the order, is exactly the negative of whatever that original area was. In other words, if you switch the order of the endpoints, the sign of the integral changes, but the value itself stays the same. That should be pretty logical. Integrating from a to a is saying if you have both of the endpoints being the same number, the answer to the integral is going to be 0. If you try and think about these two in terms of area, they should both be pretty logical. If we're going from 2 to 2, we're actually talking about a tiny little sliver with a width of 0, really. So it's not going to have any area. The last rule, the constant multiple rule, is also something that should be pretty logical if you just remember that really an integral is a limit. And if you're taking the integral of a certain function times a constant number out front, you're perfectly welcome to just treat that constant as a multiplier in front of the entire integral. In other words, the integral of a number times a function is the same thing as that number times the integral of the function. You can pull the number k all the way out front. Again, that's only if k is a number, not if it's a variable expression. Let's just test whether you understood these 3 rules. The graph below shows the area under the function square root of 25 minus x squared. We discussed in class how that's a half circle, and so this area here can be found by taking half of the area of a circle with a radius 5. Use that fact that you can very easily calculate this area to evaluate each of these integrals. Notice how they're all very close to this function, but there's something slightly changed. Right, so the first integral here is just talking about the area from -5 to 5 under the curve, which, as we discussed, is 1/2 pi r squared. In the second integral, it's exactly the same function, but the order of integration has been flipped, which means the numerical value of the integral is exactly the same as above, except it's now negative. In example 3, we're integrating from the same number to the same number, so clearly the area would be 0, because if you think about it, we're kind of trying to find an area of just a little line. Lines don't have areas. In number 4, we've got the same function as in number 1 with the same terms of integration, except we're multiplying by a constant number 8. So the numerical value of the integral is just 8 times the value of the original. In 5, we're actually also multiplying, although you have to be a little sneaky because this is the original function. It looks like it's being divided, but dividing by 6 is the same thing as multiplying by 1 over 6. So when I multiply by 1 over 6, multiply the numerator denominator, and we get 25 over 12 pi. Double check that these are easy for you. This was just the normal integral using the area. This was the order of integration rule. This was the limits when it's the same number. And then the last two you had to put together the constant multiple rule. Hopefully that's straightforward. You will need to memorize these rules, and you'll need to work to make sure you recognize what rule you're using. If you can do that, we're all set to go. Okay, there are 2 more rules that we'll talk about, and we're going to talk about them in a little more depth. The first one is the sum and difference rule. The sum and difference rule says that if the function that you're integrating inside of the integral, and the whole thing has to be multiplied times dx, if the function itself is really a sum of 2 different functions, in other words, if you can think of it as something plus something else, then you're welcome to rewrite the whole integral as 2 integrals added together. Again, if you think about the fact that really an integral is a limit of something, this should be perfectly reasonable, because you know that we're allowed to split limits as long as they both exist. Of course, the same thing is true here. If you're worried about why this works, let me show you an example by thinking about area. So let's suppose that we're taking the integral of the function sine of x plus 2. This is what that function looks like. Well, all we need to point out is that this area right here is kind of the same thing as a rectangle that looks like this at the bottom, added with this curvy function and its area on top. If you imagine stacking this function right on top here, the shading of those 2 pieces together would equal the same area as this shading. And this rectangle is precisely the area or the integral from 2 to 10 under the function 2, which is this second piece. In our case, it would be the g of x function. And this curvy area is the area under the sine function, which is kind of like what we're saying f of x would be. The original function is something plus something, so the integral of the original function is the same thing as the integral of the first piece plus the integral of the second piece. And the order doesn't really matter there because we're just adding. Let's try this out in some examples. This is a fairly common way to test your conceptual understanding of integration. We're going to evaluate each of these 4 integrals without using an antiderivative, just based on the 4 given integrals that are on the side here. So they're telling us that the integral from 2 to 5 of x is 10.5. And there's going to be some way to rewrite each of these integrals as the sum or subtraction of 2 different integrals, and that's going to help us get the numerical answer, again, without using an antiderivative. I'll do the first one with you, and then I'm going to have you try the last 3. So it should be fairly obvious that the integral from 2 to 5 of x plus 5 should be the same thing as the integral from 2 to 5 of x plus the integral from 2 to 5 of 5. Now, why would that be helpful? Well, for one thing, we know what the integral from 2 to 5 of x dx is. That's a given value. So that first integral is equal to the number 10.5. Now, I really just need to know what the second integral is. This one's not given to me, but think back a couple days. Think about what this would look like. This is the area under the curve y equals 5 from 2 to 5. It's going to be just a rectangle. Y equals 5 is a straight line. And so it's a rectangle that's 5 units high and 3 units wide. In other words, its area should be just 3 times 5, which is a very easy number to calculate. That's just 15. And so 15 plus 10.5 is going to give us a total answer of 25.5. And that's the numerical answer to this integral. Go ahead and try that same process and method for B, C, and D. You may need to be a little tricky. All right, here's the work for b. As you can see, we split it into 3 integrals, each of which is either a known number or an easily evaluable. You get 55.5. How about c? As you probably realized, c is very much the same. You split it into 2 integrals because there's 2 terms. And this time we're going to use a constant multiplier rule. Instead of putting the 2 inside of the integral, I'm allowed to just multiply it on the outside. And from there, you've got an easily identified integral, and you just multiply 2 times the value of this second integral, which was another one of our known values. Last one, d. The easy part of d was to recognize that you need to split it into 2 integrals, but this was actually kind of a test of how much you're paying attention, because notice the original terms of integration are going from 5 to 2, which is the opposite direction than we normally want to integrate, which means in order to evaluate them, or certainly in order to use the given values, which are all going from 2 to 5, we need to switch the orders of integration. If I switch the 2 and the 5, though, it means the whole numerical value of the integral is going to change sign. So I have to put a negative on the outside if I'm going to switch the top and the bottom numbers, and that's true for both of these. Having flipped the sign of the whole thing, I now have a known integral inside here, and I can just use that value, and a known integral inside here, and I can just use that value, giving me a total of negative 38.301. Okay, this should be pretty easy. Maybe you need a little practice with it, but let's learn one last rule. The last rule in this video is the additivity rule, and this is a different kind of adding than the sum and difference rule, so pay close attention here. In the sum and difference rule, if you remember, we were adding 2 functions inside of the integral. All of the integrals we worked with had the same limits of integration. Not so for the additivity rule. In the additivity rule, we're going to add 2 integrals that have different terms of integration. In other words, the intervals of the areas are different, except they share one number. The end of the first interval is the same as the start of the second interval. We could call these adjoining intervals. Visually, it means the first integral goes from, for example, 2 to 6. The second integral starts at 6 and continues on to another number. So they are 2 areas that are basically right next to each other. If we are taking the integrals of 2 areas on adjoining intervals and the actual function inside is exactly the same, we can join these 2 integrals to make one integral across the entire region. In other words, the integral from 2 to 6 plus the integral from 6 to 10 is the same thing as the integral from 2 all the way to 10 as a single integral. Let's practice this one. In these examples, we're again going to evaluate each integral without using an antiderivative, but by being a little sneaky. In this case, we're given various known integrals. Notice that the function is the same, but each integral has slightly different terms of integration. In other words, the interval over which we're finding the area is different for each of these numbers, but the function is the same, except for the last one. So let me do A with you. In A, we're asked to find the area under the e to the sine x curve between -3 and 6. First of all, notice that we don't have that exact value. So what I do have, and it's a good idea to just start with what you know, I do have a value from -3 to 0. And that's a known interval. I know what that numerical area is going to equal. Well, if I want to find the area from -3 to 6, and I know the area from -3 to 0, I just need to add another integral. What integral would I need to add? Exactly, I'd need to add the integral from 0 to 6 in order to complete the entire interval. From -3 to 0, from 0 to 6, all together makes from -3 to 6, again of the same function. The good news is I actually know the numerical value of this one as well, so the rest is a piece of cake. I add the known values and get my numerical answer for the entire interval. Since we're out of time, You should work on B, C, and D using the same strategies, and in the next video I'll pick up with the explanation of those and one more